Yay! Right. So, yeah. Today, I had something I was gonna say, but then I looked outside and I'm like, it looks like it's raining, and then I just lost my whole train of thought. So today we're going to evaluate and graph polynomial functions. Now, if you notice when you came in today, I did not put graph paper up there for you, okay? Because today's graphs are more sketches than anything. I want you to get the shape of the function, not the exact values of the function. Because some of these functions today are going to have ginormous values. Okay? All right? So let's do it. Okay? So here is the difference between a polynomial and a polynomial function. Okay? Same terms. One is written in function notation. One is written just as a polynomial. Okay? What do you see as the difference, or what's different about them, other than the fact that one's written in function notation? That's function notation. And fx is a channel on TV. F of x is what's written. Somebody said it. The equal sign. Yep. The difference is an equal sign. So a polynomial is simply just an expression. Okay. What can we do with an expression? We can't graph it. We can simplify it. What else? See, it's an expression because it doesn't have an equal sign. What else can we do with an expression? What do you mean? Can we evaluate the expression? Like, can we put, can we evaluate it if we set x is equal to 4? Evaluate 8. Yeah? Can we do anything else with it? No. Sure you could. Well, I can think of a bunch of other things, but yeah. But we'll get to those tomorrow. We can add another expression to it. We can combine expressions. We can multiply expressions. We can subtract expressions. But we'll get all that stuff tomorrow. Okay? So, a polynomial function, then, is an equation. What can we do with an equation? Is that it? What other things? The things that we can do to an expression? Okay, so let's start there. So we can simplify it. We can evaluate it. What are the new ones? We can graph it. And what was the other one you said, Noah? And we can solve it. On top of, we can add two functions together, we can subtract two functions, we can multiply two functions, we can factor a function, we can factor an expression, and so we can do all those different things with those. Okay? New terminology today. Okay? The standard form of a polynomial or a polynomial function has the terms in descending order of exponents from left to right. So what I mean by that is the very first term has the biggest exponent. Okay? Then the next term has the next biggest exponent, and the next biggest exponent, and so on and so forth, until you go all the way down until you have the smallest exponent. And then you have just whatever, if you have a number without an exponent, or without a variable, call that a constant. Okay. Now, this first term, and the reason that we do it this way, this first term with the biggest exponent tells us a bunch of stuff. So first thing that it's going to tell us is the lead coefficient. Is going to be the number in front of that term. When it's written in standard form, the lead coefficient is the number in front of the first term. It also is going to tell us the degree. The degree of a function is what we call the biggest exponent. And we'll get into the relationship with degrees and lead coefficients and graphs a little bit later on. Okay? So that's why standard form is so important for us. So let's take a moment here to reorganize this polynomial function into standard form. And then let's identify what the lead coefficient is and what the degree is. Okay. Kelly, did you have a question? Okay. Okay. Oh, okay. Can you talk to me? What do you got? Do we, well, ask them. Poll the audience.
Yep.
Do we agree with negative 5x to the fourth power first?
Yeah, I do.
Okay, so we've used up that one then. Plus 2x cubed. Or 2x to the third power. We used up that one. And minus x squared. And then plus 4. Do we agree that that is the standard form of this polynomial function?
Yeah, probably.
Okay? So with that being said, that is the standard form. What is then the lead coefficient? Hold on, I heard two different things.
Wait a second.
I heard negative 5 and I heard negative 5x. Negative 5 because it's just the number in front, right? Okay? So the lead coefficient is negative 5. What is the degree? Everybody agree on both of those accounts? I would also concur with those two. Again, we'll get to that more later on. let's talk now, and you can just sketch these right now. And we're just going to talk about different polynomial functions and what they look like and their degrees and that kind of a thing and their relationships. See if we can see a pattern. Okay? So the first one is a constant function. And the degree of a constant function is 0. Okay? Because there is no variable in there. If I were to write this as if it had a variable, it would have an exponent of 0. That's why the degree is 0. The biggest degree, or the biggest exponent, is 0. Okay? Constant functions are horizontal lines. Okay? The picture of a constant function is a horizontal line, whatever it would. So in this case, it would be -6. We go down 6 and be a horizontal line. Okay? The next one should be one that you're very familiar with at this point in time, and that is a linear function. A linear function has a degree of 1, and it forms a skew line, meaning it's not vertical or it's not horizontal. It's at some kind of an angle. Let me know if I'm going too fast through these. The next one is your old friend from Algebra 2, a quadratic function. A quadratic has a degree of 2. Okay? And does anybody remember what a quadratic function looks like? We got Bugsy? It's a U, right? Or an upside down U, right? But that's got a degree of 2. Next one is a cubic function. Cubic function has a degree of 3. Cubic functions look like that. They have a hump inside of them, or they have a change in direction. They have a valley and a hump. Depending upon how many terms come after the x cubed term will determine the depth of that hump. Next one is a quartic function. A quartic function has a degree of 4. Should be every Wausau West Warrior's favorite kind of function. Because it makes a W. I get it. Should also be every Mosinee and Marathon, but those have negative lead coefficients, so then that's why I don't care about that. That's why we're the best. We're positive. Yeah. I don't know why I didn't put it in there this time, but the next one has a degree of 5. And it is called a quintic function. Just this one. I just wanted to get to my second favorite mathematical term. Quintic.
What's your favorite?
Multiplicative.
I don't think it's really.
Whoa.
On every single one, yep. So this one's going to have two humps. A two-hump camel. Did anybody see a pattern? What do you got? I'll scroll back up, see if we can see a pattern. I'll slowly scroll. What do you mean it changes direction?
One less hump than one
Okay.
less direction.
Okay. Quintic, two humps. Going in opposite direction. Okay. All right. So one less, or what did you say, Luca? One less direction change than the degree? We'll come back to it. What I want to talk about today is I want to talk about something called end behavior. End behavior, you've already talked about this a little bit. Okay? It is, the end behavior is what the function, what the function, the true WTF,
What the function?
is
You
doing
gotta calm down. It's 20 minutes having a good time.
Okay. So it's what the function is doing on the side of the end behavior. There is specific terminologies that you have to use when dealing with end behavior. And these terminologies are non-negotiable. Roz, if you give me 5 more minutes, then you'll understand this much better. Okay? Okay? I promise. I promise. Okay? Right?
The function.
So here are 2 graphs, and you can just sketch them in your notes. Okay? You don't have to necessarily graph them, but there you should put the axes and then just kind of what they look like. Okay? So for end behavior, it is always written as x approaches positive infinity. So what this is saying right here, okay, as x approaches positive infinity, so that means x is getting bigger and bigger and bigger and bigger. On a graph, where do I find the x values? On the horizontal, right? Okay. So the whole horizontal is all of the x values. So what this is saying is as x approaches positive infinity is the right side of your graph. Okay. So if I said, what is the end behavior, like numbers 1 through 6 on this week's homework, you would first write down as x approaches positive infinity. And then you would say, well, where's my function doing? What's my function going to? F of x is going to, in this case, it's going to positive infinity because it is going up. Okay. Then, so that's the left side. Now that's the right side. Now we have to do the left side. So that says as x approaches negative infinity. So that is telling me the left side of the equation. Or excuse me, of the graph, not of the equation. And what is the function doing on the left side? The function is going to, what, Bugsy? Negative infinity because it's going down. In number 2, as x approaches positive infinity, what is your function going to? Negative infinity, because it's going down. And as x approaches negative infinity, it's going to positive infinity. The left side is going up. Okay? Now, that terminology, if you'll notice, it's exactly the same on both of them. That is the terminology for end behavior. Okay? You can't get around it. If you don't put it exactly like that, you are wrong. You're speaking a different language. Okay? You're speaking French in German class. Okay? All right? So that's the terminology that needs to be used. Okay? Let's try 2 more. I just wanted you to get that part. So that you understood left and right sides. Thanks, kiddo. Okay? Again, sketch the graph and then find me the end behavior. Okay? So as x approaches positive infinity on the left one, f of x is approaching positive infinity. As x approaches negative infinity, f of x is approaching. Both of those are going the same direction, yes. Okay. But you have to write them out separate. Right one, as x is approaching positive infinity, f of x is going to negative infinity. And as x is approaching negative infinity, f of x is going to negative infinity. Okay. Did you see a pattern yet? What do you got? That's not a pattern. Kaylee? So if it's an even degree, we go in the same direction. Both sides either go both up or both down. Okay? Odd degree, opposite. One goes up, one goes down. Okay? Anything more to the pattern? I'll go back a slide too. Anything more to the pattern? Kaylee? Okay. That does, yep, that is true. That's what I was thinking, but okay. Which side goes down?
Yeah, the right side.
All right, okay. So, first question you're going to ask yourself is, because you don't need the graph to figure out end behavior. Okay? So, highest power on these functions, odd or even, is the first question you ask yourself. If it's odd, the two sides go in opposite directions. If it's even, they go in the same direction. And that direction is determined by the lead coefficient. If the lead coefficient is positive, then the right side will go up. If the lead coefficient is negative, the right side will go down. And you will have to ask, or you'll have to give both sides as x goes to positive infinity is the right side of your graph or of your function, and as x goes to negative infinity is the left side of your function. Okay? All right. So what I would like you to do now is, one, I would like you to sketch this graph, and two, I would like you to tell me what the end behavior of this function is. Okay? So sketch, literally just a sketch. Right?
No.
No?
No, because
Why not?
Because it's a negative. The lead coefficient.
Oh, so that's now okay. Oh, we are paying attention. I was just teaching. I was making sure you were paying attention.
Yeah.
So is that better?
Yeah.
Okay. All right.
It has 5 humps.
Okay.
Oh, that's 6.
1, 2, 3, 4, 5, 6.
Boom. 1, 2, 3, 4, 5, 6.
Yeah. Okay. So our end behavior is going to read as x goes to positive infinity. My function is going to negative infinity. And as x goes to negative infinity, my function is going to positive infinity.
I'm confused.
What's up?
So, how come there's 7 humps?
There isn't 7 humps.
How come the 6? Because it's
1 less than the degree.
But how come it wasn't like that on the other one?
It was.
No, like if you go back.
If I go back to this one,
The one without the constant.
the one without any other terms behind it.
Because there were no other terms.
Right, but
The other terms don't make the hump.
okay, so that was the highest. The degree is 4, but it only has
3 humps.
So you have the opportunity for
3, because a hump is a direction change.
Right.
So as long as there's one term, it'll have the
So
maximum.
1, 2, 3.
Right. So then, if it has any terms behind it, it'll have all.
It'll have pumps. Well, it might not have all of them, but it'll have some of them. You just gotta have spot points. But again, we're just dealing with sketches. Okay? You now have enough information to do numbers 1 through 6 and 15 and 16 on your homework.
1 through 6.
1 through 6, 15 and 16.